Today, I'm speaking with Jas Semrl, lecturer of computer science at the University of the West of Scotland. Jas did his PhD in the Foundational AI CDT at UCL, and his research truly is foundational, as we'll see. Welcome, Jas.
Hi, nice to be here.
Let's jump straight in. The title of your thesis was Finite Representations in Relation Algebra. So maybe we can build this up step by step, starting with a binary relation. So what is a binary relation and how do they come into computer science?
It's a good question. Binary relations are actually quite simple. At the end of the day, it is a set of ordered pairs from a different set, and a set, for the purpose of this video, can be a collection of elements.
It's kind of abstract thinking of them as pairs, but a pair would be like the relation the son of. Then that relation consists
For
of all
example.
the pairs of a son and a parent.
Yeah, that's correct. But of course, it doesn't necessarily have to be people. It doesn't necessarily have to be any real things. Um, when you are possibly building mathematical models of the real world, at the end of the day, it's just going to be something written down on a piece of paper or stored in computer memory. So, yeah, some examples of relations could include son of or child of, parent of, that sort of thing. But it can also be things for example, before, meaning any pairs of, and I must say, any ordered pairs
Mhm.
of points in time where the first one is before the other one. And this is where the order really comes in, because you can see that if I say that yesterday is before today, that doesn't necessarily mean that today is before yesterday. In
Yeah,
fact, it's not.
yeah.
And same with my parents are my parents, but I am not their parent.
Hmm. So what would be an example of a relation in computer science?
The main example for computer science, in my opinion, would be thinking of non-deterministic programs. And let's maybe take a step back and sort of have a look at it step by step and build to it. So if you think of a computer or any machine, you can think of it as being in some sort of a state. So think of everything that's in its memory, on its hard drive, all of the buttons that have been pressed, any of that. And then a computer program is usually going to be a function, meaning that it will take that state and turn it into a different state. So, for example, if a um, a simple calculator, that's a computer, right? And I type in some input, I will expect it to turn it to something else where the result of that calculation is on the screen.
Hmm.
And this is what we'd call deterministic um, a deterministic function, or just a function, because it will take this computer from one state to another and it will always be the same thing. However, that's not necessarily always the case. Sometimes we are dealing with forms of non-determinism and randomness. So a good AI example of that would be generative AI models, where you give it the same prompt, but it might take you into two completely different states or multiple states. And I'd say that, for example, a generative AI model is actually a really good example of a relation rather than a function, because you give it some input and it won't necessarily give you the same output every time. It'll actually give you a slightly different one based on lots of random factors and how it chooses things. So this is why we need to be thinking of relations and not just functions, mathematically speaking, when we do theoretical computer science.
I see. So it's part of the definition of a function that it has one output.
Yeah, so for example, like a simple function is like, for example, plus one, right? So if I want to increment by one, 5 plus 1 is always going to be 6. It's just going to be 1. Whereas if I have something that's more of a relation, right, I can say maybe add anything between 1 and 5, and that will get us anything from 6 to 10.
I see, yeah. So a relation is like an extension of a function, a generalization of a function where you can have more than one output.
Yeah, correct, yes.
Okay, yeah, I can see now how that would be a useful notion in computer science because they come up all the time.
It really is. And then from there, you can go into lots of different directions. So you can go to spatial reasoning, you can go to temporal reasoning, you can go to what we call formal verification, rather than testing whether or not a bit of software does what it's supposed to be doing, can we prove mathematically that it does what it's supposed to be doing? Given some assumptions, of course, because we're no longer really in the real world. We're sort of like going into this abstract pen and paper world.
So normally you would want to verify a deterministic function, but using relations you can prove verification theorems about non-deterministic functions.
Yeah, correct. And that actually was, that was one of the things included in my thesis was trying to show how using relation algebra with some operations, well, we can talk about them later maybe, you can prove things about non-deterministic programs. So programs with an element of randomness and a very specific type where what we call the daemon. So imagine we have a non-deterministic program and we're interested in what happens best case scenario. So that randomness gives us something good. And this is when we in theoretical computer science would say that the angel is in control of non-determinism. But I was looking at what happens when the demon is in control of non-determinism.
Okay.
And you can show some things using relation algebra like that.
So this is like when some sorting algorithms use randomness as part of the algorithm, and you're looking at, okay, what if the random number generator that's used in the algorithm always picks the worst possible number? Like, can you still prove something about whether the program like terminates or yields a good result in a certain amount of time or whatever?
Yeah, correct. Yeah. So that in particular wasn't really anything about program performance. It was purely about correctness.
I
But
see.
yes, can we say that a non-deterministic program is still going to compute something that we want when the daemon is in charge of non-determinism?
Okay. And presumably if it works when the demon is in charge, it works when anyone else is in charge, because by definition that's the worst case.
Yeah. Yeah, correct. Yeah.
I see. Interesting. Okay, so we've got binary relations. Let's build up to relation algebras. So for that, you need to talk about how relations can be combined one with another. So should we describe a simple example, maybe with a family relation, and then maybe move a bit towards computer science?
Yeah, sure. So as I said earlier, relations are sets of pairs. So you can call it the left side and the right side. We are talking about relations over the same set. So, for example, if we go back to people, um, it's the same set of all people that we're talking about when we describe a parent relation. So, because they are sets, we can do things like the union, for example, for a parent relation. You can do a union of, for example, and this always gets a little bit controversial. So I use for example a birth parent and a adoptive parent as the union to make together parents. And I'm sure I missed a few people, but let's oversimplify it and say, the relation parent is going to be the union of adoptive parent and birth parent.
Right, so you've got one relation which is birth parent of, so person A is birth
Yes,
parent of person B, and then you've got another relation which is adoptive parent of, person
yes,
A is adoptive parent of person B, and then you can form a new relation which is just parent of, and you are A is parent of B if either A is adoptive parent of B or A is birth parent of B.
yeah, and maybe another point to add here is that there can be overlap between those two because this is not an exclusive or, it's just an or. So, for example, union of brother of and sibling of, and I assume that brother of is fully included in the sibling of, would then just be a sibling of.
Right, right. And that brings us also to orders. right? You could partially order binary relations. So
Yeah,
you can say that brother of that relation is in some sense smaller than sibling of that relation.
yes, yeah, correct. So the moment you've got union, and you can add intersection as well, just for fun. The intersection of brother of and sibling of is going to be just the sibling, oh sorry, just the brother of, whereas the union of the two of them is going to be the sibling of.
Mm.
Now, the moment you've got either intersection or union, you can start talking about ordering as well, where you're talking about brother being contained in sibling,
Hmm.
but of course not vice versa. Another possible one to quickly talk about is the empty relation, meaning no pairs included, just an empty set. I hope I'm not doing too much like assuming here, but let's say that we've got brother and sister as relation, and we take an intersection of the two, that would be the empty relation.
Right, right.
Maybe we can talk about the time relations as well. So if you think of sort of the timeline, and we're gonna like stay clear of the controversial topics, maybe. So let's say that we've got something like before, which means um, point A in time is before point B in time. So the union of before and after is going to be all pairs of points where they're not equal, essentially.
Hmm. Hmm.
Whereas if I say the intersection of before and after, that is going to be the empty relation where we've got no points connected to each other. And then as a complement of the empty one, we can also get the full relation, and similarly, you can get a complement of any relation. So if I look at the relation before, the complement of that will be after or at the same time.
Hmm. Hmm. Yeah, maybe we should go to the familial relationship for that one because that overlaps with converse, right, in the time one.
No, not necessarily. So the converse of before is going to be after.
Right,
So
right.
let's maybe start with the definition of a converse. So a converse is the is the is the relation of all pairs where we have flipped around essentially which one comes first and which one comes second in of the original relation. So, for example, a parent, if we take the converse of that, we'll get a child. And for time, the converse of before is going to be after.
Okay, so there's converse and then there's also negation, right? So converse of parent of is child of, the relation goes the other way. And then
Yes,
complement or negation of parent of is just not parent of. So
yes,
I'm not
exactly.
I'm not the parent of you, for example.
And similarly, I am not the parent of you. The converse of before will be after, whereas the complement of before is going to be either at the same time or after.
Hmm. Hmm. So then the idea is like, okay, if we can pin down all these definitions and properties of relations, like what is the converse, how do you chain relations together, etc., then you can study all of this in the abstract, and then this will give you powerful tools to apply in particular cases. So just like in linear algebra, you nail down all the definitions and the axioms of what it means to be a vector space, and then you prove some stuff in there, and then you have these big theorems that you can just plonk on and use it in mathematics, physics, computer science, and loads of other places.
Yes, and I feel like relation algebra is definitely sort of similar in that level as being this abstract tool where you are talking about things like this and possibly a generalization of vector spaces, a generalization of other forms of algebra in universal algebra. Um, maybe a story for another time.
So I just want to give people a flavor of like what these theorems within relation algebra might look like. Oh, so first of all, yeah, a relation algebra is just a collection of relations uh, with a specification of like how they interact and also like some operators which transform one relation into another. So we've already talked about some of these, right? Like converse, it takes one relation and produces another relation where everything's switched around.
Yeah, so let me just put some corrections in for clarity.
Okay.
Maybe I'll give a definition of a proper relation algebra, if that's okay.
Yeah.
So, and this is a proper or a concrete relation algebra is going to be defined by some set over which we are defining these relations, and then we say, okay, well, we're going to take some relations over these sets, and that is going to be our collection of relations. And then we're going to define a few operations. So some of them we already talked about. We get the empty relation, we get the complement, we get the union of them. We also get the meet of them for free from complement and join, and we also get the universal relation for free from that. Then we talk about the one relation we haven't talked about yet, which is the essentially the equals or the diagonal relation, meaning just all of the pairs that are, so for example, me and myself in the same pair. So all of the pairs of elements of that big set with itself, that is going to be the diagonal, the equals, or the identity relation,
Hmm.
as we like to call it. We've talked about converse, so that is flipping the pairs around. And then finally, there is the composition of relations. And the composition of relations is actually really similar to the composition of functions. So think of it as doing one relation and then another one after it. In the case of family relations, that would be, for example, the parent composed with a sister, that would be an aunt.
Hmm.
Now, it's really important to say, okay, we've got parents composed with sister, that is going to be an aunt. Whereas if I say sister composed with parent, that is not going to be an aunt.
Right.
So it's not commutative. It's the order does matter.
Yeah. Yeah. Okay. So for many people, it would be a parent, also a parent of themselves or a step parent.
Yeah.
Okay. All right. So that's a relation algebra. And then I asked Claude for a baby theorem that you could prove in relation algebra. And then what it gave me was that if you have two relations, relation A and relation B, then if relation A is contained in relation B, then the converse of relation A is contained in the converse of relation B. So you can prove this just purely abstractly. And then when you go down to like the concrete level, you realize this totally makes sense. So for example, if relation A is child of, so person one is child of person two, and relation B is a descendant of, right? So A is contained in B. If you're a child of someone, you're also a descendant of them. Then if you take the converses of both, so the conversive is a child of, flip it round, is a parent of, and the converse of is a descendant of, flip it round, is an ancestor of, then you get the same containment, right? If you're a parent of someone, then you're also an ancestor of them.
Yeah, so that on a concrete level, that is an example of if A contained in B, then A converse contained in B converse.
Hmm. So then you like go away with your pen and paper and just derive these theorems from the axioms and hopefully provide tools that are actually useful in the real world for computer science.
Yeah, so this is where we start going away from the proper relation algebras into the abstract world, where well, I mean, I suppose even, I mean, okay, maybe I'm being a little bit unfair here because even proper relation algebras with sets and relations over those sets are already one abstraction up from the real world.
Yeah,
But
but we're
then you
going
go one
further.
abstraction, yeah, we're going one abstraction up, further up, and we say, okay, we now just don't really care if these elements of our algebra are relations anymore. We are now actually just saying we've got some A, B, C, D in that set, possibly infinitely many, possibly uncountably many. Once you get to those sort of dimensions, it's not particularly useful for computer science anymore.
Okay.
Let's say that you got a collection of those, and you say, okay, well, I'm going to define these operations. So I know that A union B is C, but I don't actually know if there are any points or how this can be represented as a proper relation algebra where these A, B's, and C's actually get a proper set and they become relations over that set.
I see.
And this is one abstraction up. And even though we're going further up in being abstract, it's actually still quite useful in computer science, especially because what can happen over here is that you can have a situation where you have finitely many relations, but once you go to the proper setting, any real any real representation with proper relations will necessarily have to be over an infinite set. So it's actually a tool for you to reason about infinite concepts, if you will, with a finite set.
I see. I see. So maybe I can repeat that back to you and see if I've understood it. So like
Yeah,
the lowest level of thinking about relations is where we have concrete things that we're talking about, right? Like people. And then we talk about relations like familial relations over those. And then going one level higher, it's like we don't care what the actual things that are related are. We just call them elements of a set. And then the relations are just sets of ordered pairs, right? We say like, oh, this element is related to this element, but we don't actually care what the element is. And then you go one level higher, and instead of like a collection of elements with relations over them, you have a collection of relations. And you don't even care like what the relation actually is. You just care about how they interact. Like, what's the
yeah,
converse of this relation? Is the converse of relation A relation Q? Or if I combine relation A and B, which relation do I get? Do I get relation C? And so this is like the very high level of abstraction that you're working on.
yeah. And so, for example, if we go to the relation algebra of familial relationships, right? And let's say that, we've got like a simple model of them where, there's a few like brother, sister, parents, child. So we know how these interact with each other, and you know, that is a very small set of relations. But if we wanted to go back to the concrete place, you all of a sudden don't have a handful of relations, you have currently about 8 billion people in that set. So the size difference is massive. As I said, in some cases, it will be the case that the size difference is so massive that it's actually impossible, even for very small algebras or small collections of relations and how they interact with each other, find a finite set over
Hmm.
which you can represent it. And yeah, maybe if we talk about my results later, we can talk about
Yeah,
we
yeah.
can talk about one of those.
Yeah, so let me see if I test my understanding again. So you've got this you go up from this level of here are my concrete relations over set elements that I don't care about to here's my collection of relations and how they interact. And so someone might come to you now with a collection of relations and how they interact and be like, oh, look, this is fun. I've got a relation algebra here. Look at how I can combine these. And then you might be suspicious and be like, okay, these things, yeah, they walk like a duck. They walk like a relation and they quack like a relation. But are they actually relations? Like, can I actually find a set of elements and then define actual relations, sets of ordered pairs, such that the things that you're calling relations correspond to these actual relations? And then the second question is like, okay, how big does this set need to be? Can I get away with a finite set? So, like with familial relations, if someone comes to you with a collection of relations that quack and walk like familial relations, you can be like, okay, well, there are 8 billion people on the world. It works with those. But if someone comes to you with a more esoteric collection of relations then it might not work for a finite element for a finite set. You might need an infinite set to be able to like concretely define all those relations.
Yeah, exactly. And this is probably where we get to the point where we have to acknowledge that this is probably the main reason why the adoption of binary relations in computer science has been slow, because now we get to the point where we have to admit and be honest about relation algebra and say, look, we have to admit that relation algebra is computationally speaking, incredibly badly behaved. And what we mean by that is that it is mathematically impossible to have a computer program that will take a finite relation algebra and tell you, yes, this does walk and quack like a relation. It is actually impossible for it's one of those problems that we would call undecidable. So there is no computer program that could decide whether or not this actually is representable as a proper relation algebra.
Right. So you've got these things that like so you've got these things that walk and quack like relations, and you want to know, okay, are there concrete relations that they can correspond to, they could correspond to, and you say
Yes.
in that sense the relation algebra is representable, and you're
Yes,
saying there's
correct.
no
Yes.
computer program, there does not exist a computer program such that you can feed it a relation algebra and it will spit out yes or no depending on whether it's representable.
Yeah, I mean it all goes it all goes back to sort of proving it goes back to proving in the early days of computer science that, for example, you don't have a computer program that can determine whether or not a different computer program is going to compute something in a finite amount of time. So this is the class of problems we're talking about, problems that are incredibly difficult to solve, um, and you can, of course, approximate them. And quite often, what artificial intelligence models are actually an approximation of something that is actually undecidable in the first place,
Right.
which is probably why we've gotten quite far. And it's not necessarily going to be the case. It's not necessarily going to be the case that it's very difficult to prove whether or not a relation algebra, a particular one, corresponds to a proper one. So to this proper collection of proper relations and
Hmm.
not just some interactions of relations. But this is the case that in the most general sense, you cannot have a computer program that will, in a finite amount of time, determine whether or not this can be represented.
Right. So you can write a computer program that will tell you whether some programs halt, and likewise you can write a computer program that will tell you that some relation algebras are representable, but no computer program will do it for all of them.
Yeah, correct. Yeah.
Okay. So then in particular, so you were really focusing on finite representability. So whether it can be represented by a finite set of elements. So why were you so concerned about that?
Yeah, so finite representations are one of those things in relation algebras that weren't that well researched, but they are actually quite important. There is one really important problem that is still open, and I don't know. I'm sure someone will solve it at some point. But as far as I know, it's still open whether or not the problem of figuring out whether a proper relation algebra can be represented finitely. So whether it can be represented over a finite set. So for example, you give some familiar relations and say, okay, can I find a finite set of people that will behave in this way? Um, there, it's not known whether there could be a computer program that could decide that, and that is still one of the unknown problems. And In general, finite representability was not as well researched as the other parts of it, but there were some very important questions, and finite representability is also really useful for computer science. So if you know that you can switch between something that is sort of abstract and something proper within some bounds of finite representability, usually quite bad bounds. We're talking exponential bounds, but it's still useful. And sometimes it's okay to know, okay, with very little needed, I can actually show that I will not get finite representability. And negative results are also really important because not only because it's fun, with a very stretchy definition of fun, but it's important as possibly a warning sign saying, if you're trying to do something in terms of the applications in computer science or anywhere else really, maybe don't try this one because it's actually computationally and exceptionally badly behaved.
Right, right. So I suppose in computer science, you can only represent finitely many things on a computer. So if you're studying a relation algebra that's not finitely representable, then you're proving theorems about things that are not ever going to be useful in computer science.
So, yes and no. I mean, you need to ask yourself, do I actually do I actually need do I actually need all the points represented? Um, when you are reasoning about time, for example, the relation algebra that you use for temporal reasoning, so before, after, at the same time, not at the same time, before or at the same time, that sort of thing. That relation algebra is actually a prime example of something that cannot be finitely representable.
Hmm.
And it is fun to prove it. Temporal relation algebras and especially temporal reasoning and using these temporal relations in the context, for example, of modal logic did actually eventually lead to things like reinforcement learning, where you've got chess masters and go masters being beaten by computers. This is now 10 years, 10 years in the past for AI, and it feels like incredibly outdated in comparison to all
Right.
of the generative AI we get now.
Yeah, I see. So, like, I suppose we still prove things about infinite dimensional vector spaces, so functional analysis. And in some sense, you only need finitely many functions because you can only represent finitely many on a computer. But it's still, that doesn't stop it being a very powerful tool.
Yeah, for sure. And it's really just about finding good and bad behavior and being aware of what that behavior is if you do actually want to do any sort of computer sciencey things with it. Because one of the important things if you are using an approach is you need to know its limitations.
All right, so we talked about representability. You mentioned that you can't write a computer program that will take in a relation algebra and spit out whether it's representable or not. But it's unknown whether you can write a computer program that will take in a relation algebra and spit out whether it's finitely representable or not.
Yes.
So we talked about decidability and undecidability. Let's now move on to the Hirsch conjecture, which was one of your supervisor's conjectures that you made progress on in the thesis. So can you describe what the Hirsch conjecture is?
Yeah, so earlier we defined proper relation algebra as a collection of relations, and then in addition to that, you get a few extra operations. And now we know that in general, it won't be the case that if you have a finite collection of relations, you can also represent it finitely. And the conjecture was that depending on which of those operations you decide not to care about, sort of eliminate, the conjecture was that if you are willing to eliminate the intersection and the composition, then you should get finite representability for all finite algebras. So imagine you have something like that, where you got a relation algebra and you just say, okay, well, now I'm interested in whether or not I can represent it finitely, but all of a sudden I actually don't really care about the intersection. I don't really I don't really care about that. Can I represent it now?
Hmm.
And the conjecture was that yes, as long as you're either willing to sacrifice composition or intersection, you should get finite representability.
Okay, so someone comes to you with a relation algebra and it's got all of these relations and all of these operators, and they say, can it be finitely represented? And you're like, well, if you throw away intersection and you throw away composition,
Just one of them, really.
okay, if you throw away at least one
Yeah.
of those, then I can finitely represent it for you. That was the conjecture.
Yes. Yes. And it turned out to be slightly wrong.
Okay.
So it was known that if you have both the intersection and composition that you care about, then it's sufficient for those two to be included to get non-finite representability.
Hmm.
And one of my results in the thesis is there's another condition that is equally sort of minimal in that sense. And you say, well, you need negation and you need composition, and that is also enough to give non-finite representability. And the way that that was actually proved was with the algebra I was talking about earlier, which is
The
the one
temporal one.
for temporal one. Yes. If I have a collection of binary relations and I care about the negation and I care about, or the complement, and I care about the composition, it's enough to say that I know about that. It will have to be non-finitely representable. The algebra of spatial and temporal reasoning. Sorry, just the temporal one. We sometimes call it the point algebra because it's not necessarily just for time. It's for anything that can be represented on a line, really, as these relations being what we would call a total order,
Hmm.
or like less than, or before,
Right, right.
after.
So where
Yeah.
you're set is everything sitting on a line in a neat order.
Yeah, it does have to be infinite,
Hmm.
that one.
So what was your reaction when you proved it, and what was your supervisor's reaction?
At that point, we already knew that the conjecture was slightly wrong
Hmm.
because there was a different result. Maybe this is the point where it's important to mention that negation can be defined in two, or the complement can be defined in two different ways in relation algebra, and I think it's okay to leave it at that. But we call it relative and absolute complementation. And the reason why that is goes into universal algebra and what we call varieties and quasi-varieties, and maybe we can leave that for another day.
Yeah, that sounds like a level of abstraction I'm not quite ready for.
But we knew that if we have the ordering, so the inclusion of relation and negation or complementation and composition, we knew that if that complementation is absolute, then it will definitely not be the case. And then actually recently in a collaboration between, so that's maybe like one of the most recent collaborations between my supervisor and Marcel Jackson from Latrobe and myself. Um, there's also the result that if we take the other complementation, the absolute one, which we don't usually talk about, we not only get that result, but we also get undecidability. So not only the undecidability of representation problem, but also the undecidability of the finite representation problem.
Right, right.
Maybe I should have mentioned that it was known for some cases where you say, okay, you know what, I don't care about this, I don't care about that. In some of those cases, it is actually already known that we have the undecidability of finite representation as such. So it wouldn't be a surprise if it turns out to be the case for um, the actual big relation algebras with all of the operations as well.
Yeah, so it's roughly intuitive, right? That like if you're trying to represent a relation algebra, then the more operators you have, then the more rules you're trying to satisfy with your representation. And so the harder it's going to be to find a representation.
Yes, but also not necessarily because sometimes you have lots of rules and then adding that extra operator will actually simplify lots of things because maybe there is an axiom or a formula that is generally true that is very easy to describe when you have an operator, but when you don't have it, you sort of need to create almost like a proxy for that
Okay,
sort of
okay,
behavior to happen. So sacrificing some operations can lead to things getting simplified, but it
hmm
can also lead to things actually getting more complicated.
okay, okay. Wow. So that was the Hirsch conjecture and the progress you made on there, just connected to yeah, finite representability. Let's talk a bit about finite axiomatizability. So how I understand this is it's like another level above, right? Where below you had like your set of relations and how they interact, just like as a big long list. But another way of doing this is um, you might have infinitely many relations and they might interact in complicated ways. And you have a list of rules of how your relations interact. So maybe you're less concerned with the actual relations now, and you're now just concerned with how they interact, the rules of interaction. So these are called the axioms of how your relations interact. And for a given relation algebra, you might be interested in, okay, can I write down in finitely many formulas, finitely many axioms, how the relations interact? Is that a good
Yeah,
explanation of finite
that is a
axiomatizability?
very good explanation. Yes, that is precisely how it works. And maybe something that seems sort of difficult to prove would be actually because, if you have a finite list of rules and you can say that these are sufficient to say, okay, yes, this will then be representable, it almost feels like there is an intuitive way of how to show that a finite list of rules is sufficient. But what's maybe more interesting is that you can also use some tricks, some mathsy tricks, to actually show that it's impossible, right? It's impossible to do that because proving something is impossible is, like, even philosophically speaking, um, the much more difficult task, but it can be done. Just like possibly saying things like, okay, can we have a computer program that does that? And we say no, mathematically impossible. It's the same with these finite axiomatizations. Um, we know that if we have this finite set of rules, that is a sufficient condition for decidability of the representation problem because if you have a finite set of rules and a finite algebra, you can just test it against the rules and you know whether or not it's going to be finitely representable.
Okay, okay, that makes me understand why you're so interested in finite axiomatizability now, because it helps so much with this
Yeah,
other problem. Okay, so what did you prove about finite axiomatizability?
in my PhD thesis, I've actually mostly proven non-finite axiomatizability. However, I can think of at least one result where I was able to, where I was able to well, I was able to prove finite axiomatizability. So let's maybe start with some negative results. Um, it is my understanding that I found the first example of the set of operations we care about, where you get no finite axiomatizability, but this finite representation property, meaning that every finite one that is representable will also be finitely representable. Um, and that actually had something to do with these algebras that are describing programs where the daemon is in charge of non-determinism, to bring it back to the beginning
Oh
of the
wow,
interview.
okay.
And the way you define some operations when the daemon is in charge of non-determinism is actually not going to necessarily be any of the operations that I have described at the beginning, but rather combinations of those um, of those um, of those um, the combinations of those operations or predicates. So, for example, a predicate of ordering we've talked about, and you can think of how a non-deterministic program is going to be included in a different non-deterministic program. So, think of, for example, I don't know, let's go back to ChatGPT, right? And let's say you've got a different computer program or a different AI model that can produce all of the same answers from a single prompt, but a few more.
Mhm.
That ChatGPT will be included in that other model,
Okay.
for
Well,
example.
maybe another
Now,
example would be like you could
yes,
set the temperature to 0 so that it always picks the most likely word, and then you have a deterministic program, and
yes,
that's also a relation. It's a proper function now, but it's
yeah,
a relation. And it's
it
a
is.
subset of the ChatGPT with a non-zero temperature.
Yes, correct. Yes.
Okay.
Now, what is ordering when the demon is actually in charge of non-determinism. And maybe let's not go into the proper definition of what it is, but it's actually not going to be exactly the same sort of ordering. It's actually going to be based off of what we would call the demonic choice, which is the union, right? We know the union. We talked about, like, for example, the union of two computer programs that are non-deterministic is just a computer program that can output any any of those outputs. Now, imagine that you give the daemon the choice of two programs, and that is your union. The daemon's union is not going to be the same as this union. And similarly for demonic order, it won't be exactly the same as this angelic order, if you want to call it that. And when you have relations closed under this demonic or with this demonic order included and closed under composition, um, and those are the only two predicates and operations that you care about, in that case, you are actually going to get non-finite axiomatizability of representability. But if something is representable and it is finite, it will also have a finite representation.
Okay. Gosh, that was a lot. um, maybe I can pick up on a few threads that I understand. So, like, you want to say you've got ordering of relations, right? Like one, like the ChatGPT with zero temperature is contained in the other in the ChatGPT with non-zero temperature, and then so that's like the ordinary ordering we would think about, and then you can think about the demonic version of this ordering relation, where the ChatGPT with non-zero temperature picks the worst word at every step.
Yeah, possibly something like that, yes.
Okay. And then ChatGPT with zero temperature would not be included in the demonic ChatGPT.
Um, yeah, I think the likelihood of that being the case would be very low, yes.
Okay. Okay, so your relations are non-deterministic functions. You're modifying your operators to always pick the worst thing, which makes them demonic. So you found that when you like modified these operators to use always the demonic version, then you suddenly get lots of results about all three of these things. So finite axiomatizability, finite representability, and decidability. Was that quite a surprise when all of these things sort of flowed out of this assumption?
It wasn't really a surprise, but I was very happy with the way that the result came out. It was definitely one of the first things I've shown during like the first years of my PhD, and it was a really big sense of accomplishment that, it was for the first time actually generating previously unknown mathematical knowledge, which I'd be lying if I said didn't feel amazing. But just maybe a quick correction of that, because it is important to say that yes, things were modified. Things were modified for the demonic part. However, there is a there is an important distinction between what was modified and what wasn't modified. So the actual composition of programs actually remained angelic. So that means if you do the same thing twice, so one program followed by another, the angel was still in control of non-determinism there.
Hmm.
However, if you are in a situation where you're doing this demonic choice or demonic meat or demonic ordering, we are talking about the demon being in charge of non-determinism. The case where you have the demon in charge of both composing programs, so running them one after the other, and also the demonic ordering itself is actually a little bit better behaved. In fact, it behaves exactly in the same way as its fully angelic counterpart, which has been known to be finitely axiomatizable and finitely representable since about the 70s, well before this demonic relation algebra came in.
So are you still working on these questions now, or is your research taking a different form?
Yeah, so I'm probably not as focused on finite representability anymore, even though it is still a major part of my research focus, all of these problems. In fact, quite a lot of Hirsch's conjecture is still completely unknown.
Hmm.
There's also all these questions about finite representability, finite axiomatizability that I have an urge to answer, you know, haven't quite answered yet. But I have also tried to go in different directions. So at the moment, I need to start packing because I'm going to Johannesburg tonight, which I'm quite happy about.
Wow.
Yeah, so I'm visiting Andrew Craig and Claudette Robinson from the University of Johannesburg. We're going to be working on a variation of relation algebra called quasi-relation algebra or distributive quasi-relation algebra. The way you can think of it is possibly a generalization of relation algebra. So like if we're going in the abstraction levels, it goes
Even more
it
general.
goes even more general. But what we're trying to do is we're trying to provide a game theoretic framework for proving some results. So my PhD supervisor, Robin Hirsch, together with Ian Hopkinson, of I believe Imperial College in London, maybe about 20 years ago, 25 now, they sort of set up this game theoretic approach to proving lots of things in relation algebra, where rather than proving things I mean, it is still purely mathematically, but you can turn the proof into a two-player game where you
Okay.
essentially have to only show either that there's a winning strategy for a certain game, or there is or that there is a collection of algebras for which there maybe isn't a winning strategy, but you can maybe play it for a little longer every single time, and that is how you can prove things like non-finite axiomatizability through
Is
game theory.
the advantage of this approach that you don't have to be constructive anymore? Because in some games you can prove there's a winning strategy without actually writing down what the winning strategy is.
Yeah, so in my experience, you would have to be constructive with winning strategies in general. It does help, but I'm sure that in the future there's gonna be some results where maybe you'll be able to do it non-constructively. But speaking of game theory for proving things in relation algebra, something I currently have a grant application I really hope it gets accepted for is I would also try and see if it's possible to do some computational approaches to these winning strategies for some of the smaller finite algebras. So when you think of games, you very often think of things like reinforcement learning. And recently, some people have been turning some graph theory, which is a different but closely related part of mathematics. They have been turning those problems into games, and they were able to then train the reinforcement learning algorithms on them to try and learn those games and actually find some counterexamples. And I think that with this game theoretic approach, if if we tried hard enough, it might be possible to use reinforcement learning to try and find some representations. Because the thing about relation algebra is we talked about how, there's not a lot known, and it actually is the case that for even some very, very small relation algebras, we still do not know whether or not they actually have a representation. Do they have a finite one? Any of that? And yeah, then there's the addition of all of these variations of relation algebras that I may not have been working on during my PhD that I am sort of more interested in now. But roughly speaking, I'm still in the relation algebraic field of research.
So you could ultimately imagine AI being trained not to play a game like chess, but to play a game where one tries to construct a finite representation and the other one tries to how does the other one try and foil
Yeah,
their attempt?
so so the two players are usually called Abelard and Eloise, named after the two I believe it was a nun and a monk in the 14th century, and fact check me on this, please. But they sort of had this lovely love affair where they were like talking through letters, and there's all those letters preserved. And Abelard is the player that says, this is to be a representation. I want to see what we call a witness for a certain operation. And Eloise is then the one trying to amend this set of relations to actually witness that operation. And step by step, they go towards constructing this finite representation. And of course, if Eloise, if she's got a winning strategy, she will prove that the algebra is representable.
I see. So Avalon is sort of making the demands and saying, this is what we need to do
Yes,
next, or this is a requirement we need to finitely represent it. And then Eloise
yes, it's
is actually doing the work of constructing it.
yeah, and it's also it's quite a neat little little like naming convention that you can do for the two. Even though Eloise actually starts with an H because they were French monks, so a
Of
French
course.
monk and a nun, so that the A and the E just silent. But we like to say that Abelard is the for all player because the for all symbol is just an upside down A, and exist is
Nice.
Eloise. And in fact, what they are doing is Abelard is saying, for all operations, I want to see something. And Eloise is the
Mm.
one pointing to it saying, yes, there exists that, or possibly it doesn't. And you can actually, with that two-player game, you can actually show that some really, really small relation algebras are actually not representable. And you can do it in other ways as well, but you can actually just say Abelard in this case has a winning strategy,
Mm.
and that is enough of a proof to say that even very small relation algebra is in fact non-representable.
So when's this game coming to Steam? When can I download it?
I think the version 0.0 is nearly ready. I'm I'm sure there's a market for it. It'll be you, me, and possibly one other person playing it.
I'm sure this is what happens in the breaks at theoretical computer science conferences.
Yeah, yeah, it's pretty much as that. We don't play chess. We play the representation games. I wish I were joking.
Well, I've really enjoyed chatting about your research. It's a level of abstraction I don't often encounter, and it's been great fun. So thanks for coming on to talk about it.
Yeah, thanks for having me. It was great fun. It was amazing. Thank you so much.